So absolute value means how far a number is from 0 on the number line, and there's no negatives allowed. What we mean by that is imagine, and I'll draw it at the top here, imagine I have a number line, and at the center of that number line, it's 0. So we can think about it as integers. And so it's from 0, and this is 5, and this is negative 5. And it doesn't matter whether you're 5 units to the left of the line or you're 5 units to the right of the line. Your absolute distance, if you were to end up here or here, is going to be 5. And so to represent this phenomenon, where we don't care whether you're to the left or to the right, but how far you actually are, we look at that straight distance from 0 to negative 5 or 0 to 5 as just 5 units, or absolute value of 5. Now this can make sense if you think about it like distance. You wouldn't say that I'm negative 5 kilometers from school if you lived over here. So let's pretend your house was over here and this is the school. You would just say, if somebody asked you how far is your house from the school, you would just say, oh, it's about 5. And that would be the same if your house was over here. You would just say 5 kilometers. So to represent an absolute distance, or I should say just a pure distance, whether left or right, doesn't matter, we say that this is your absolute value of 5. So we write absolute value, or to represent that it doesn't matter whether our x is negative or positive, we use these absolute value bars. And so whenever you see a value of x inside those bars, it doesn't matter what the integer sign is. Now the parent function for your absolute value, and this is before transformations, is going to be f at x is equal to absolute value x. And so how does this work? Well, if we look at, let's say, the absolute value of 5 and what that equals, that is just going to equal 5. If I go minus 5 inside those absolute value bars, it's still going to equal 5. If I write 0 inside these value bars, it's going to equal 0. Whether it is a positive sign, a negative sign, or no sign, whatever that x value is before the sign, it is going to be the output. And so what we would say is, if we're thinking about it as a function, remember that f at x is your y value. So if I ask you for what's the y value or the f at x when your x value is negative 4. Well, for your absolute value, your f at x is just going to be 4. Now, if we write that in function terms, I would say that the f at negative 4 for this function, negative 4, is going to just be 4. It's the same thing if I were to write f at x is equal to, let's say, 2, and I want to know what the value of f at 2 is. Well, it would just be 2, irregardless of the sign. Now, if we were to graph the absolute value function here, given that this stands for whatever value of x, be it negative or positive, is going to be the value of y, and we fill it in as such, so x, negative 3, f at x would be 3, negative 2 would be 2, negative 1 would be 1, 0 would be 0, and then 1 would be 1, 2 would be 2, and 3 would be 3. And if we were to plot those points, let's start at negative 3, we'd say that it would be at negative 3, you would have y value at 3, so I'd plot a point here. At negative 2, there'd be a y value, this should be over here. There'd be a y value of 2, and at negative 1, there'd be a y value of 1, and at 0, 0. Now, if I go and plot, if I connect these dots like this, and if I were to plot the other side, right, so the second half of that list, let's say in light green, actually we'll do it in red. So 0, 0, 1, over here is going to be 1. 2 is going to be 2. Add 3 is going to be 3. We could see that it makes a perfect V. Now, more importantly, we can see that no matter what the x values are, whether it's -1 or +1, they have the same y value. And that's true with all these values. If you go -2 and +2, they all have the exact same y values. Now, what we also notice is that other than just plotting the points, the absolute value function has another origin that results in the same graph. And if we were to plug in, let's say -3, so if I go root -3 squared, that would be, -3 squared is 9, and then root 9 would be 3. And if I do -2 squared, that's 4, and then the root of that would be 2. I would notice that I have the same exact values. And so what we can say, and if we were to plot these, you get the exact same graphs. What we could say is that if f at x is equal to root x squared, and we could also say that f at x is equal to absolute value x, and those two give us the exact same graph, then we could say that absolute value of x is equal to the square root of x squared, where the negatives and the positives of the x values don't matter at all, and hence we get the same graph. And so because of the shared similarity between the two functions, where essentially your absolute value function is just the root of your quadratic function, like your quadratic function, we can see over here that your absolute value functions, I'm going to write f at x, when f at x is equal to absolute value x, that these functions are symmetric. I can see that the left side is symmetric to the right side, that they have a vertex, just like a quadratic has a vertex, and the vertex is right over here. We can see that they have a change in direction. So they have a minimum and a maximum, and they can open down or open up. And so in this case, if it opens upwards, then this would be a minimum value. And then, like our quadratic functions, they respond to transformations in a very similar way. And if we could say that the general function of f at x is equal to -x squared produces a parabola that opens downwards, then f at x, when it's equal to the negative of the absolute value of x, this too would produce a absolute value function that opens downwards as well, but it would be in the V format. So how do we perform simple operations with the absolute value functions? Let's say for these two examples here that x is equal to 3. Well, what we do is we go f at 3, if I'm looking at the first example, is going to be equal to 3 minus 3. That is going to be absolute value of 0, which means that f at 3 is just going to be equal to 0 because the absolute value of 0 is 0. Now the same thing is going to be said over here. I'm going to go f at 3 is equal to 3 minus 2 plus 4, which means that it's going to be absolute value of 1 plus 4. Now, whether that is positive 1 or negative 1, it doesn't matter. So it'll just be 1 plus 4 And that means that the value of f at x at 3 is going to be 5 in this case. Now what happens if, let's say for c, I have a function like this, where it is absolute value of x minus 3, and then let's say plus 2, but my x value is going to be, or let's say I'm going to write in function notation where I want to know what the value of this function is when f at -4. So what happens when the input of x is -4? Well, I would go -4 minus 3, absolute value of that plus 2, and I would work out the absolute value of this. And so f at -4 is equal to -4 minus 3 is -7. So you can see that I'm treating these absolute value bars like brackets here. And then plus 2. Well, remember that the absolute value of -7 is just 7. So that would really be the same as 7 plus 2. And then that would equal 9.